Today we're going to talk about an ideal gas, meaning if the world was perfect, how would gases behave? What would they look like? And he gives you actually on page 300 characteristics of what an ideal gas would be. So we're going to go through those because I want to make sure you understand what an ideal gas actually is. So the first characteristic says an ideal gas is one in which the molecules or atoms that make up the gas occupy no volume. Okay? That may initially sound really strange because a gas is matter. Matter has to have volume. It has to have mass. It has to have volume, or it's not matter. It has to take up space. If you think about a gas, though, in a gas, the molecules are very, very, very far apart from each other. And so if you kind of take an extrapolation, you kind of say, well, if I extend that out, what would that look like? Because the molecules are so far apart, it's almost as if there's no volume. That's really kind of what we're saying here. Letter B says the molecules or atoms that make up the gas are not attracted to each other. Again, in real life, that's not true because molecules and atoms are attracted to each other. But again, because they're so far apart, molecules of a gas aren't going to be attracted to each other very much just because they don't have an opportunity to get real close to each other like the molecules are going to do in a solid or in a liquid. Okay? The third one is one that we really talk about quite a bit more in physics, which vast majority of you probably have not had yet. It says the collisions that occur between the molecules or atoms that make up the gas are elastic. What does that mean? Well, if you think about running into maybe you get up in the middle of the night and you don't turn the light on and then you ram into the wall. You're going to know you hit the wall because you're likely going to hurt yourself. You're going to hear a thud. Depending on how hard you run into it, the wall may shake a little bit. That collision was not elastic because energy was transferred from you to the wall if it vibrated. Maybe it got transferred from you to your nose if you hit it hard enough and you smashed your nose and you hurt yourself. So those collisions were not elastic. In an elastic collision, what happens is two things hit each other and they bounce off and there's no transfer of energy. Again, it's practically impossible for that to happen. It is impossible for it to happen, but you can get a pretty decent picture of what it would look like if you've ever played pool and those balls, when they hit each other, they bounce off of each other. There's not a whole lot of energy that's lost. There's still some because you can still hear them hit each other. But an elastic collision is one where they completely bounce off and there's no change of energy involved. Again, in reality, elastic collisions are not possible, but they can get really, really close to that. This would also be true not only for collisions between the molecules of the gas itself, but for any collision that happens between the molecules and the container that it is hitting. Now, there is no such thing as an ideal gas. You can't have a gas that has no volume. You can't have completely elastic collisions. You can't have no attraction. So why do we talk about an ideal gas? Well, it's because in a gas, the molecules are so far apart from each other that they almost are going to behave as if they are ideal. It's so close that the approximations that we make can generally be pretty valid. So, what conditions would have to be true in order for us to have an ideal gas or to be able to use the conditions so that we can assume that the gas is going to behave in an ideal fashion? Well, we need to look at the three characteristics that we've already talked about. First of all, pressure. If we don't want the molecules to be banging into each other very often so that we don't have to worry about collisions, we want that pressure to be very, very low. Okay, so a gas will behave most like an ideal gas if it is at a low pressure. Okay, similarly, we want the temperature to be high in comparison because at a high temperature, gases are going to tend to occupy a higher volume. And that's really the whole goal that we're looking at. We want the volume that they're occupying to be very large. Okay? And so if we want the volume to be large, the temperature, if you have a high temperature, it's going to tend to push that volume large. If you want the pressure low, the volume's going to have to be large. And gas molecules also come in all sorts of different sizes. And so the smaller that the molecules are, the less often they're going to collide with each other. And so really, you also want your gas molecules to be very, very small, again, in comparison. Okay? Now, I just want to point out that I know this high temperature is probably one where you're scratching your head and going, okay, that seems counterintuitive. It seems like I wouldn't want the molecules to be moving very much so that they're not running into each other. But if you remember the relationships, when temperature goes up, volume goes up. And so what I'm really looking for is a large volume so that I'm not going to have very many collisions happening. Okay, so just to summarize, gases will behave most like an ideal gas if your pressure's low, your temperature and volume are high, and your molecules are very, very small. If those things are true, then we can relate things using the ideal gas law, which says if I multiply the pressure and the volume together, that relates to actually the amount of gas that I have, or the number of moles that I have, as long as I have a constant in here so I can take care of all these different units that I'm going to have, because I've got to be able to cancel those units out somehow. Okay? Now, the ideal gas constant is 0.0821 liter atmosphere over mole Kelvin. Okay, so because the ideal gas constant has these particular units, anytime you use this, your volume has to be in liters, your pressure has to be in atmospheres, and your temperature has to be in Kelvin. You also can't use grams. You have to have everything converted to moles in order for this relationship to be able to work. Again, this is how a gas behaves if conditions are ideal. Okay. What you will notice here is that there's no requirement in there for what the gas is. We had said that the molecules ideally need to be small, but all gases, no matter what their identity, whether it's argon or chlorine gas or carbon monoxide gas, it doesn't matter what gas we're talking about, you can still use this equation for it, because basically all gases are going to behave the same no matter what their identity is. Okay, so we do have a sample problem to go through here. So if you've got your sheet with all the sample problems on it, a gas is in a 12.2 liter container at a pressure of 13.5 atmospheres and a temperature of 25 degrees Celsius. How many moles of gas are present? Okay. So this is a simple plug and chug problem. It tells me that my pressure was 13.5 atmospheres, so I'll plug that in over here. It tells me that I have a volume of 12.2 liters. I don't know what the number of moles is, so that's the variable that I have. The ideal gas constant, 0.0821 liter atmosphere over mole Kelvin. And then the temperature says it's 25 degrees Celsius, but if you recall, we have to have it in Kelvin. So I have to use, I have to add 273.15 to that. So 25 plus 273.15 will give me 298 Kelvin. Okay. Remember that significant figures tells me that since 25 doesn't have any numbers after the decimal point, once I add it to the 273.15, I won't have any numbers after the decimal point here either. Okay, so in order to solve this, you're going to take 13.5 times 12.2 divided by 0.0821 divided by 298, and then you're going to have a number of moles of 6.73 moles. Okay? Because the atmospheres cancels out, the liters cancels out, and the Kelvin will cancel out with that ideal gas constant. All right? So those are how to work ideal gas problem laws.